Okay, so now to get into number 2, this one says to investigate how increases in environmental temperatures affect the metabolism of certain organisms, researchers incubated liver cells from toads at different temperatures and measured two markers of metabolic activity seen in table 1. You have rate of oxygen consumption and rate of ATP synthesis. Okay, so here's your table here. You've got your two metabolic markers, rate of oxygen consumption, rate of ATP synthesis, and then you have them at different temperatures. You've got 20, 25, and 30 degrees Celsius. Okay, so part A actually has nothing to do with this table. It's a pretty general question, just like the last one, which says describe the role of water in the hydrolysis of ATP. Now, you guys should know the role of water in like a hydrolysis reaction in general, but they wanted it to be specific to ATP. Now, the big thing that happens with ATP is that ATP is converted to ADP, and that's how the energy is released. So you have an adenosine here, and then you have 3 phosphates attached to it. 2, 3. And then when you add water to the equation, like this, what's going to happen is you're going to cleave this bond here, just like it does for any other macromolecule like carbohydrates, proteins. The water is going to split that part, and then you're going to end up with ADP, so adenosine diphosphate with a loose phosphate here. Okay, so if I were to actually write that out, the role of water is to break, I'm not entirely sure how specific they want you to go with this, so I'm going to say break the covalent bond, because it is a covalent bond, between the third and second phosphate. This is going to release the energy, and what it is also going to do is it's going to attach an OH to one of the molecules and a hydrogen to the other, and that's how it facilitates. So OH on one of them, and then H on other. That's how it breaks that bond, by giving one an OH and one an H. They have their full octet, so they're not going to have to make that bond anymore. So again, don't know how specific they would want it, but this is the answer to this question. So breaking the covalent bond between that third and second phosphate, and in addition with H2O, you're going to have that break apart into OH and H and attach to one here and then one here, and that's going to break a covalent bond. Okay, so the next part says, for part B, it says, using the template in the space provided for your response, construct a bar graph that represents the data shown in table 1. Your graph should be appropriately plotted and labeled. Okay, so they tell you what type of graph to use, which is very beneficial. And so you're going to be doing a bar graph with table 1, which is right here. They had you use the template that was given. I don't have the exact template, but I was told that it's about 20 by 30. So we're going to zoom this in, and we're going to construct this bar graph. Now, what's really important for these are identifying what your X and Y axes are, because most of your marks are going to be from actually just labeling the graph and constructing it. So your x-axis is always your independent variable, so that's the thing that you're changing, okay? And then your y-axis is the result, or what you're looking at. So in this case, our x-axis is going to be temperature, okay? Because that's the thing what we're changing. We're trying to see how the change in temperature affects our metabolic markers. So you're going to have temperature down here, and then you're going to have your metabolic markers here. So there's a couple different ways you can do these, because you do need to plot oxygen consumption and ATP synthesis separately. I was looking, and I saw some people had opted to do like a double bar graph. There are a couple different ways to do this. I'm going to show you guys the most simple option and what I feel like most students would have done. But again, there are probably a couple different ways if you wanted to do like oxygen on this side and then ATP on this side. It does just get an extra complicated. So I'll show you the easiest way that I would recommend doing it. So for this one, I would put on your y-axis your metabolic marker. So again, always important to put your titles here as well as units. So metabolic marker, and then please, please, please put the units. You won't get a mark unless you put the units. So it is in nanomole. Again, you can just copy it directly from the table. Milligrams of, and please write the whole thing, mitochondrial protein, and then plus minus 2 standard errors. Okay. Alrighty, so they usually don't give you marks for putting a title on the top, but if you were to put a title on the top, you could just copy this right here, rate of oxygen consumption and ATP synthesis at different temperatures, maybe put it just in case, but they usually don't give you marks for that. Now, in terms of how I'm going to set up this graph, you have your 3 different measurements. So you have 20 degrees, 25 degrees, and 30 degrees. Okay, so let's do this. We'll put 25 degrees here. It's just most logical. Oops. Okay, actually, backtrack that. So the best way to do these is I'll put 20 degrees Celsius here, I'll put 25 degrees Celsius here, and then 30 here. And then for these ones going up, it's really important that you choose the correct scale. So again, I believe that they gave you a 20 by 30. So there's a couple different scales in which you can do this. As long as it makes logical sense, they'll give you the mark. So I would say if they gave you 30 on the y-axis, you could either go up by 1 or by 2. Either would have been fine. And what you could have also done, which they don't really teach you, and would have also been acceptable, is because the first number doesn't start, at 1, the first lowest number starts at 12.6. You could also start your graph at, 12. Okay, and then just go up by 1s for here. You usually put a little symbol here that just indicates that you skipped a chunk. But just for the sake of this, I'm going to just do the whole entire graph. But again, if you did that little skip, as long as you plotted it correctly, you would have been fine. So I'm going to go with the fact that each one of these squares is 1. So you don't need to plot everything. So 2, 4, 6, 8, 10. And then our highest number here is 22.1, so I'd probably just go up to 24. You can do it all the way to the top. It's not completely necessary. Okay, so now let's start with our first numbers. So we're going to start with our 20-degree measurements. Okay, so these are our 20 degrees measurements from the tables. You've got the first one at 12.8 and the next one at 12.6. Okay, so for these ones, you're doing a double bar graph. So you're stacking them beside each other. You could also technically stack them on top of each other, or again, like I said, do a double bar graph with oxygen on one side and ATP on the other. This is just the most simple way to do it. However, if you do it this way, you need to include a legend, and I'll show you. So 12.8 for oxygen consumption. So this won't be the most accurate graph, but if you have 12 here, 12.8 should be around here. You can make them single bar, double bar, it doesn't really matter, whatever works best for you. So I just did 2 across just to make them a little bit easier to see. And then the other important thing is you have to put your standard error in. So here it's 2.2. Now they won't go right up until the millimeter, so as long as you're pretty close with it, so 2.2 is going to get you to 15 upwards, so you're around here, and then 2.2 down gives you about 10.6. Yes. Okay. And then your other one is 12.6, so we'll put it slightly lower. Again, as long as it's somewhat accurately plotted, they will give you the marks for it, and then plus or minus 1.6. So we'll go up 1.6 here, and then 1.6 down. Okay. Now, just to make sure that you can distinguish between these two graphs, because they are 2 different measurements, one's for oxygen and one's for ATP, you want to either color one in or, put a pattern on one of them. I'm just going to color in one of them like this. This would have been more than enough. and leave the other one blank, just so you can distinguish between them. And then we'll put the legend in as well. So for 25 degrees, we've got 16.5 and then 16.8. So these are fairly close numbers. I don't know if they allow you different colors, but simply coloring in one or like putting hatch marks in it would have been fine. So we've got 16.5. So this one over here should be around, oops, make it a little lower. 16.5 should be around here. And plus or minus 2, so it should be here, to 18.5, this. And then 16.8, we'll put it slightly higher, and then plus or minus 2 again. And then making sure to color in the one that is for oxygen consumption. And then finally, your 30 degrees, you should have 22.1 and then 21.07. Okay, so 22.1 around here. And then plus or minus 0.7, so it's a little bit smaller. Again, they're not going to measure it to the millimeter, but as long as it falls within an appropriate range, it should be fine. So that's about 0.7. And then 21.07 should be pretty much like the exact same. Or sorry, oh no, this is not 22.07, it's 21.07, my bad. So 21.07 should be 1 lower. So right about here. And then plus or minus 0.8, that. Okay, and then drag that down, and then making sure to color in. So these ones have smaller error bars. If you were to draw bigger error bars for these ones, they would mark you wrong. So just keep them relatively proportional. So then you have to write a legend if you're going to do it this way. Frankly, whichever, like unless you do the oxygen on one side and ATP on the other, you have to put a legend, especially if you're also doing a stacked bar graph. But this is the simplest bar graph that you can do for these ones. And I always say make it as simple as possible for these ones. So you would do a legend where you put this little colored in one, and then you would put, we made this one rate of oxygen consumption. So rate of oxygen consumption. You don't have to put the units here because you already put them here. You can just in case, but all they really want to know is which one's oxygen and which one is ATP. So this one's going to be rate of ATP synthesis. Okay, so that is this one. So you will get marks for properly labeling the X and the Y axis. So you should have temperature, and then you should have metabolic markers with the units. You need to accurately plot these with accurate error bars. And then if you do this type of graph, you have to make sure that you include your legend as well. So this is it all graphed. Okay, so that takes care of number 1. Number 2 says, based on the data provided, determine the temperature in Celsius at which the rate of oxygen consumption is different from the rate of oxygen consumption at 25 degrees Celsius. Okay, so they're just asking you to determine, so they don't need an explanation. They're really just looking for a value. So rate of oxygen consumption that is different from the rate of oxygen consumption at 25 degrees Celsius. Let's go back to our chart. They already told you that you're looking at 25 degrees Celsius and you're looking at rate of oxygen consumption. So this is really just your ability to point it out on the table, which is this one right here. So rate of oxygen consumption at 25 degrees. They're asking you which rate of oxygen consumption is different. So frankly, there's only two options for this one. It's either this one or this one. You're looking for which one is different, which is a strange way of phrasing it, but they're looking for basically statistically significant, which requires you to know what your error bars mean. So for this one, you have 12.8 plus or minus 2.2. So 12.8 plus or minus 2.2. That means that this can range anywhere from, let's see, so 12.8 minus 2.2 would be 10.6. And then, yeah, that would take us to 15. So that's the range for this one. And then for the 25 degrees, oops, so I'll just put 20 degrees here. And again, you didn't need to write out all of this. I'm just putting the solutions. 25 degrees, you've got 16.5 plus or minus 2.0. And so that gives you a range of 14.5 to 18.5. So these ones actually do overlap because this one goes 10.6 to 15 and this one goes 14.5 to 18.5. So they actually overlap. And what that means is that distance between them is actually not significant. So there's no significant difference between 20 and 25 because their ranges overlap. We need to do it for 30 as well, just to double check. So let's put this over here. So for 30 degrees, you've got 22.1 plus or minus 0.7. So that is going to give you a range of 21.4 to 22.8. And so none of these values overlap. So these values of 30 overlap with your values over here of 25. This one ends at 18.5 and this one starts at 21.4. So these two are significantly different from each other because their ranges don't overlap. So the answer for this one is going to be, you're looking for the temperature at which there's a difference. Your temperature at which there is a difference is 30 degrees Celsius. So that's all you had to put, 30 degrees Celsius. Okay, so the next part says for C part 1, describe on the data in table 1 the effect of temperature on the rate of ATP synthesis in liver cells from toads. Okay, let's go back to this bigger one. So you're looking at temperature and I believe ATP synthesis. So temperature on the rate of ATP synthesis. Okay, so we're increasing temperature this way, and we're not looking at oxygen consumption, we're only looking at ATP synthesis, and it looks like as temperature increases, you're also going to have ATP synthesis increase as well. So 12.6, 16.8, 21.07, that's increasing, and it's increasing as your temperature is increasing. So you can say, for this one, you can say positive correlation, you can say direct comparison. I'm just going to say increase in temp, again, write it in full sentences, equals increase in ATP synthesis. Okay, and then for number 2, it says, based on the data in table 1, calculate the average amount of oxygen consumed in nanomoles for 10 milligrams of mitochondrial protein after 10 minutes at 25 degrees Celsius. So I've seen a couple different answers for this one. I'll put what I personally think the answer is. However, I would obviously wait until the actual marking scheme comes out. But they're asking you for the oxygen consumed at 25 degrees Celsius. And then they're giving you different units. So let's look at it, what it is currently, and then we'll just convert the units is all you have to do. So oxygen at 25 degrees Celsius. So our oxygen at 25 degrees Celsius is this number right here, which is 16.5, and then make sure you take note of the units here because that's what's the most important. Okay, so you've got 16.5. They're looking for average amount, so you don't really need to consider the standard error for this one. So I'm just going to leave that out. I'm pretty sure you can just ignore the standard error for this. Nanomoles per min per milligram. Okay, so nanomoles per min per milligram. Okay, so this is what it currently is. Now they're asking you for 10 milligrams for 10 minutes. Okay, so we're looking at 10 minutes and you're looking at 10 milligrams. Right? You're keeping, and then you're looking for how the 16.5 would change. So for this one, you would multiply it by 10 and then you would multiply it by 10 again, because you're looking for, here you're looking at 1 minute, but here you're looking at 10 minutes, so multiply by 10. And then here you're looking at 1 milligram, but now you're looking at 10 milligrams, so then you would multiply that by another 10. I saw some students do it only by 110. However, I believe since two of the measurements are changing, you would multiply it by 100 instead of just 10. So your answer for this one would be, so 16.5 times 10 times 10. It should give you 1650. Okay. Animals. Okay. Again, I'm going to wait for the answers to come out, but since you are changing two of the units by 10, you would likely have to multiply both of them. Okay. Now, for the last part of this question, part D, the first part says oligomycin is a compound that can block the channel protein function of ATP synthase. Predict the effects of using oligomycin on the proton gradient across the inner mitochondrial membrane. So this one, again, is more of a theory question. I'll add another slide here. So oligomycin is going to block the function of ATP synthase. So it's really important, obviously, that you know about ATP synthase and what the proton gradient does in the mitochondrial membrane, and then you have to justify it. So this is D. Let me draw a little diagram here. So you have your mitochondria like this, and then we have your inner membrane with the cristae. This. Now you have your ETC, which is going to be a bunch of proteins along here. And what they're going to do is they're going to pump H plus from here, from the matrix into the inner membrane space. And that's what builds up that proton gradient. So you're going to have a really high amount of hydrogen in your inner membrane. Okay. Now you build up that gradient for the sole purpose of this protein here, which is going to be our ATP synthase. Your ATP synthase should have the hydrogens come back through, and that's what drives the generation of ATP, right? So you're pumping H plus into the inner mitochondrial membrane, and then the H plus flows back into the matrix through ATP synthase. However, they're saying that oligomycin is blocking ATP synthase from working. So they're asking you what would happen to the proton gradient if this was not functioning. So this is not functioning because of oligomycin. So if you had oligomycin, you would basically have all the H plus build up in that inner membrane and it wouldn't be able to come back through. So there's probably a couple different things that you can say for this. I'll put everything that I think is appropriate. So the H plus gradient would build up in the inner membrane. However, you would not be able to sort of relieve that gradient. So cannot relieve gradient. The H plus can't flow back through the ATP synthase. So that would cause a couple things to happen. So they would have probably accepted any of these. So the pH of the inner mitochondrial membrane would decrease. So pH of inner membrane would decrease. They're asking you more so for the proton gradient. So this is kind of an after effect. I'm taking it a little bit farther, so I'd be curious to see the answer guide. But in terms of the effect on the proton gradient, you would have the proton gradient build up in the inner membrane and then it would just stay there. You wouldn't be able to relieve it in any way. So you would just have your proton gradient basically constantly on. So pH of inner membrane would decrease, and then you would have less ATP synthesis because that driving of the H plus through ATP synthesis is what powers ATP synthesis. So less ATP. And you basically would not be able to diffuse the gradient or turn the gradient off. Okay, So that's the answer for D, for both part 1 and 2. Now, that is the end of number 2 for the AP exam. That brings us to the end of the long questions.